let's jump right into this explainer. Today, we're unpacking a concept that is absolutely foundational in the world of industrial tech. I mean, think about all those incredible automated systems around us, right? From the massive robotic arms in car plants to the automated valves at your local water facility. Now, we hear a ton about the brains of the operation, the computers, the PLCs, but if the PLC is the brain making all those complex decisions, well, the actuator is the muscle. It's the actual thing doing the heavy lifting, the turning, the pushing, the pulling. Literally, without actuators, even the most advanced AI would just be paralyzed. It couldn't do a thing. So let's explore how these mechanical muscles actually work.
Here's our quick roadmap for today. We'll kick things off with what an actuator actually is. Then look at the different types and how they work. After that, we'll see how they integrate into automation systems, check out some real-world applications, and talk about keeping them maintained. And finally, stick around because we're wrapping up with a real-world interview prep question. Okay, let's dive into this and start with the basics. Section 1. What is an actuator? The foundational moving parts of automation.
So, at its core, an actuator is a vital component of a machine responsible for moving and controlling a mechanism. Basically, it converts energy into physical, mechanical motion. Think of it like your own body. When you want to pick up your coffee mug, your brain sends an electrical signal, but it's your muscles that consume energy to physically contract and lift that mug. It's the exact same thing on a factory floor. A control system sends a signal and the actuator consumes some form of energy. Maybe it's electricity, maybe compressed air or pressurized fluid, and it creates that physical movement. It's literally the bridge between digital commands and physical reality.
All right, let's move on and see how these different muscles get their power. Section 2, actuator types and principles.
Now, what's really interesting about this slide is the trade-offs. Engineers have to choose the exact right muscle for the job. First up, we've got electric actuators. These run directly on electricity, and their biggest pro? Insane precision. If a robotic arm needs to stop at a microscopic point, electric is for sure the way to go. But they do have a higher initial cost. Then we have pneumatic actuators. These use compressed air. Think of them as the sprinters of the group. They're fast, they're simple, and they're very clean. The catch is that since air is compressible, they just can't push as hard. They give you lower force. And finally, hydraulic actuators. These use pressurized fluid, usually oil, and man, these are the heavy lifters. They generate absolutely massive amounts of force. Think of a giant excavator. The downside is they can leak, and they need a lot of extra gear like pumps and reservoirs. Oh, and by the way, all these types generally come in two movement styles. Linear, which is just pushing and pulling in a straight line, and rotary, which spins like a valve handle. Matching that energy source and movement style to the job, that's the real art of automation design.
But an actuator on its own is basically just raw potential. Let's see how it connects. Section 3. Integration with automation systems. Connecting the brain to the muscle. Like we said, an actuator needs instructions. It has to fit into a broader, smart system to actually be useful. So here is exactly how that signal journey happens. Step 1. Sensors collect field data. The system needs eyes and ears, right? This might be a temperature sensor in a giant vat of liquid or a proximity sensor watching boxes on a conveyor belt. Step 2. That data travels to the brain. The PLC or programmable logic controller processes the data. Often this is overseen by a huge SCADA system, which is supervisory control and data acquisition. The PLC crunches the logic and fires off a command. Sometimes that command even goes through a VFD, a variable frequency drive, just to dial in the exact motor speed of an electric actuator. And finally, step 3, the actuator executes the physical movement. It gets the command and actually opens the cooling valve or pushes the box. It is this beautiful, seamless loop of sensing, thinking, and acting.
Okay, enough theory. Let's see this out in the wild. Section 4, real-world industry applications. Actuators in action across diverse sectors.
And this brilliantly illustrates just how everywhere this tech really is. I mean, they are quietly working all around us. In heavy industry, they're handling control valve automation, directing oil, gas, and water through massive pipelines. In manufacturing, they're running conveyor systems and packaging machines, sorting boxes at lightning speed. They're literally the joints of industrial robotics powering smart factories. But get this, it's not just factories. In smart agriculture, they automatically pop open greenhouse vents when it gets too hot. And here's a wild fact. Modern solar farms use incredibly precise actuators for solar tracking. They tilt these massive, heavy solar panels just millimeters at a time to perfectly follow the sun all day long. Oh, and if you've ever tapped a button on your phone to lower your smart blinds at home, yep, that's a tiny electric actuator doing the work.
But
mechanical parts do wear down over time. Let's move into the health phase of this equipment. Section 5. Troubleshooting and maintenance. Keeping the system healthy and safe.
When things go wrong, it's a big deal. A seized actuator can literally halt an entire multi-million-dollar production line. So proactive troubleshooting is totally vital. If you're working with pneumatics, honestly, a lot of the time technicians just use their ears. You just listen for that hiss of an air leak. For hydraulics, you're looking out for oil drips or watching for a sudden drop in pressure. And for electric, you might be checking blown fuses, feeling for an overheating motor, or inspecting the communication cables going back to the PLC. Routine maintenance is all about lubricating those moving parts, swapping out seals before they bust, and calibrating everything so it moves exactly as far as the PLC thinks it is. But above everything else, safety first. You are dealing with highly pressurized air, hot fluids, high-voltage electricity, and machines that can move with bone-crushing force. Every single technician absolutely must know proper lockout and tagout procedures. You have to make sure every ounce of stored energy is released before you ever put your hands near an actuator.
So the crucial point is understanding not just what these components are, but how you actually apply that knowledge out in the field. Let's hit Section 6, Interview Prep and DEVI. Time for a quick pop quiz.
Okay, picture this. You're sitting in a job interview for an automation engineer role, and they drop this question on you. In a high-load, heavy-lifting application, why would you choose a hydraulic actuator over a pneumatic one? Take a quick second, think back to that table we looked at earlier. Got it? The answer all comes down to fluid mechanics. Pneumatic systems use air, and air is compressible. So under a massive, heavy load, that air just squishes, giving you a spongy movement and really capping your total force. But hydraulic systems use liquid, oil, and liquids basically do not compress. When you push hydraulic fluid into a cylinder, it translates directly into immense, rigid, unyielding force. So for heavy lifting, hydraulics are really the only choice.
So just to wrap things up, actuators are the essential muscles of automation. Choosing electric, pneumatic, or hydraulic just depends on if you need precision, speed, or pure force. And they rely entirely on that seamless loop of communication with sensors and PLCs to do their jobs. Now, if you are looking to integrate these kinds of smart systems, whether we're talking industrial automation, PLCs, SCADA, AI, the industrial Internet of Things, smart agriculture, home automation, or solar, you really need to check out DEVI Automation Solutions. They offer comprehensive consulting across all these sectors. If you found this explainer helpful, please go ahead and hit like, share, and subscribe. And for any automation consulting, you can email them directly at deviautomationsolutions@gmail.com.
And let me leave you with a fun little thought before we go. Automation isn't just for massive factories, right? It's about saving human time and energy. So, if you had the perfect actuator, completely hooked up and perfectly programmed by a PLC, what repetitive, mundane task in your daily life would you automate first? Taking out the trash? Folding laundry? The possibilities really are endless. Thanks so much for joining me on this explainer, and keep exploring the incredible world of technology.